The temperature of a substance is a measure of the average kinetic energy of the particles in that substance. So let's imagine we're studying a monoatomic gas, like helium. Now, a monoatomic gas is a gas containing particles of a single atom, and therefore we can simplify things a bit and treat these gas atoms as point-like particles. And these point-like particles do not rotate, they do not vibrate, and they don't have any intermolecular interactions with other gas particles. And what this means is there is no attractive or repulsive force between the atoms of gas. So this gas can be simplified to an ideal gas. And even though they don't have any attractive or repulsive forces between them, when they do collide, their collisions would be perfectly elastic. So due to this lack of intermolecular interactions for this ideal gas, we can say that there's no potential energy in this gas. And it will become clear what this means in a minute. So the temperature of this gas can be completely described by the average translational kinetic energy of the atoms in this gas. If we add more energy to this gas, the atoms on average will move faster. And if energy was to be removed from this gas, the average velocity of the atoms will be lower. And for an ideal gas like this, we can say that the temperature is equal to the gas's internal energy. And what is internal energy? Well, for all substances, including ideal gases, the internal energy of a substance comes from the random motion of its particles and the potential energy that results in the distances and alignments between particles. Now, an ideal gas doesn't have these intermolecular interactions, but other substances do. Solids and liquids do have this potential energy. So for more complex substances, such as liquids and solids and molecular gases consist of molecules of more than one atom. So for example, carbon dioxide contains a carbon atom linked to two oxygen atoms. So for these more complex substances, the temperature of the substance, in other words, the average translational kinetic energy of the particles, is only a small part of the internal energy of the substance. Some of this internal energy consists of the vibrational and rotational kinetic energy of molecules. So molecules, which are more complex than our monoatomic example at the beginning, will be able to rotate and vibrate in various ways. And it takes energy for them to rotate like this or vibrate. And this is also a small part of the internal energy of the substance. And the final part of this internal energy consists of this potential energy associated with the intermolecular attractive forces between atoms and molecules of solids and liquids. So for example, molecules of water exhibit hydrogen bonding between the molecules of water. And energy must be put into the water to separate these molecules of water, giving the water added potential energy. Now, the internal energy of a substance is proportional to the substance's temperature. And what we mean by this is that if we increase the internal energy by a certain amount, then the temperature will raise in proportion to that amount. But when the substance is changing phase, and it's going from a solid phase to a liquid phase, or if it's going from liquid to a gas, then energy is required to break the bonds that are holding the particles together. So during a phase change, the temperature remains constant, but the potential energy of the substance increases, and so does the internal energy. And in the next few lessons, we'll talk about phase changes in more detail. Now, if we had a thermometer that's at room temperature, say at 25 degrees Celsius or 77 degrees Fahrenheit, and we plunge this into a glass of ice cold water, the thermal energy will be transferred to the glass of water from the thermometer, causing the thermometer to cool down. But as the thermometer is in the process of losing thermal energy, the water will raise in temperature by a very small amount. After a couple of minutes, the water and the thermometer will reach a state of thermal equilibrium, which is the state in which two bodies in physical contact with each other have identical temperatures. Now, if the glass of ice water is large enough, the thermometer's initial thermal energy would not affect the water's temperature that much, so the temperature reading on the thermometer would be a close reflection of the temperature of the ice-cold water. So what would likely happen if our thermometer had a very high temperature, for example 65 degrees Celsius or 149 degrees Fahrenheit, and then we place it into a very small amount of ice water, say 10 millimeters of ice-cold water? What would happen to this small amount of water? So because our thermometer now has more thermal energy, as the thermometer and ice-cold water come in contact, there is a flow of thermal energy from the thermometer to the ice water until the two physical systems approach thermal equilibrium. So because there's a small amount of water, this water will likely raise in temperature above its initial state, and this will mean that the temperature reading will not be a true reflection of the initial temperature of the ice-cold water. The temperature scales most widely used today are the Fahrenheit, Celsius and Kelvin scales, and it's important to be able to convert between them. To convert degrees Celsius to degrees Fahrenheit, we can use this formula, where the temperature in Fahrenheit is equal to 9/5 multiplied by the temperature in Celsius plus 32. So for example, if we got a temperature of 25 degrees Celsius and we plug this value into our formula here, we get a value of 77 degrees Fahrenheit. Now if we want to reverse this and convert degrees Fahrenheit into degrees Celsius, we can simply rearrange this equation. So if we minus both sides of the equation by 32 here, then multiply this expression in brackets by 5, and then divide both sides of the equation by 9, we isolate the temperature in Celsius. So 100 degrees Fahrenheit, when we plug this into our equation, is equal to 37.8 degrees Celsius, to 3 significant figures. Now the Kelvin scale is used extensively in scientific work, and it's an absolute temperature scale defined to have 0 Kelvin as the lowest possible temperature. So where does this absolute zero temperature come from? Well, the concept of absolute zero arises from the behaviour of gases. When we cool down a variety of gases at a constant volume, so the volume here doesn't change, when we cool down the gas, the pressure falls in a linear fashion. In fact, for these various gases, the pressure extrapolates to 0 at the same temperature. So even though it becomes increasingly difficult to reach this absolute zero temperature of minus 273.15 degrees, in fact it's impossible to reach this temperature, but we can get very close to it if we trace back this linear gradient here for each of the gases. They converge at this absolute zero temperature, at zero pressure. So in other words, this extrapolation suggests that there's a lowest temperature, and we call this absolute zero. So how do we convert Celsius into Kelvin? Well, we can use this equation here, and all we need to do is plug in our Celsius value in the TC variable here and add the constant value 273.15 to get the Kelvin value.